Let's go through an example of the method of partial fractions for doing integral in the case where we have a repeated linear factor. So first of all, what do we mean by a repeated linear factor? That means when we factor the polynomial in the denominator, in this case the denominator is already factored, we have this repeated linear factor. In this case, the x plus 1 factor is repeated because the factorization has x plus 1 squared, meaning x plus 1 times x plus 1. In that case, the partial fraction decomposition of this rational function, which is the integrand, is going to have a constant coefficient over the non-repeated linear factor, but then we need two separate terms for the fact that this linear factor is repeated twice. So we have a term b over x plus 1 for the first time it's repeated, and then we have c over x plus 1 squared because it's repeated twice. So we need to solve for a, b, and c now. How do we solve for a, b, and c? Well, the first step should be familiar from examples where we have just distinct linear factors. The first step is to multiply through by the denominator on the left-hand side. So we multiply through by this denominator, right? That clears the fraction on the left-hand side, and then what happens on the right-hand side is common factors cancel, right? So for the first term, the x minus 1 factors cancel, and what we're left with is x plus 1 squared. Now what's going to happen when we multiply that second b term by the denominator of the left-hand side? So just one x plus 1 term is going to cancel, and so what we're going to be left with is b times x minus 1, and then still one remaining x plus 1 term. For the final term, when we multiply that c term by the denominator of the left-hand side, both x plus 1 terms cancel, x plus 1 squared cancels, and so we just have an x minus 1 term, which is attached to that c coefficient. Okay, so now how are we going to solve for these coefficients a, b, and c, right? That's the main step with these partial fractions problems. So for some of these, we can use the usual method that we do, which is plugging in a certain value of x, which is going to zero out certain terms on the left-hand side. So note that if we plug in x equals minus 1, that's going to zero out this term and zero out this term. So if we plug in x equals minus 1, that's actually going to let us solve for c. Okay, so let's do that first. On the left-hand side, we have minus 1 squared plus 11 times minus 1, right? We're just plugging in minus 1 into the left-hand side. On the right-hand side, we said that this entire term gets zeroed out and this entire term gets zeroed out, again, because of the x plus 1 factors that are there. When we plug in minus 1, they go to 0. So what's left over is c times minus 1 minus minus 1. So simplifying this, on the left-hand side, we have 1 minus 11. On the right-hand side, we've got minus 2c. So we get minus 10 equals minus 2c. So we get c equals 5. Okay, that lets us figure out what c is. Now, we said we can zero out terms by plugging in x equals 1. That's going to zero out the b term, and because of this x minus 1 term here, that's going to zero out this whole term. So if we plug in x equals positive 1, that should actually let us solve for a. On the left-hand side, we get 1 squared plus 11 times 1. On the left-hand side, everything goes to 0 except the a term, which is 1 plus 1 squared. Again, plugging in x equals 1. So on the left-hand side here, we've got 12, right? 1 plus 11. On the right-hand side here, we have 2 squared, which is 4, so 4a, dividing both sides by 4, we get a equals 3. Okay, so we've got two of the coefficients. Now the last question is, how do we get b? Now you note that we can't use the same technique because the only way we can zero out terms up here is by plugging in x equals 1 or x equals minus 1, but both of those, in both cases, as we saw, that also zeroes out the b term, so that won't work. So I prefer to use this method of substitution, which is basically pick another value of x and just plug it in, right? Since we've got a and since we've got c, we can use those values, right? So we've got, and let's just plug in another number. Let's plug in x equals 0 into both sides. On the left-hand side, obviously it's 0, right? We've got x squared plus 11x on the left-hand side. We plug in x equals 0, it's equal to 0. On the right-hand side, we've got a, which is 3, times 0 plus 1 squared. So we've got, I'll write it all out, so we're just following along the top line and just plugging in x equals 0. So we've got a is 3 times 0 plus 1 squared. We've got b times 0 minus 1, 0 plus 1, and then we've got c, which is 5 times 0 minus 1. So if you work this all out, what you end up with here is you have, so now we can just simplify that equation to solve for b, right? What do we get? 0 equals 3 minus b plus, let's see, minus 5, so that implies that b equals, what do we have, minus 2. Sorry, that last bit at the end of solving for b got smudged a little bit. So just to summarize, we've got the partial fractions decomposition now, right? This is what we started with. We solve for a equals 3. We solve for b equals minus 2. And we solve for c equals 5. All right, so here's the partial fractions decomposition. So what does that get us? Well, recall that we were trying to do the integral of this whole thing. I'll rewrite it again for you. Right? We were trying to do the integral of this. So that means we can do the integral of the right-hand side here. So, and that's going to be simpler. We can integrate term by term. Right? We're going to see that we can integrate this term. We can integrate this term. And we can integrate this term. Sorry, that got squeezed in there. There should be a dx in there. Okay, so what are these? So these are actually integrals that you should be fairly familiar with at this point. These are both examples of natural log when you do the antiderivative, right? You can see this if you do a substitution with u equals x minus 1 in this case, or u equals x plus 1 in the second case. In each case, what you end up with is, let's keep the constant 3, right? That was the constant in the numerator of that first term. And then the natural log of what we have in the denominator, right? Similarly, the second integral, the antiderivative is minus 2, again, the constant from the numerator, times the natural log of absolute value of x plus 1. Now for the last term, what we have actually is, let me rewrite this last term. It's 5, and then we've got x plus 1 to the minus 2 dx. Okay? So this is actually just a backwards power rule. Again, if you want to write it out in every last detail, you could do a substitution u equals x plus 1. And then you'd basically have u to the minus 2. And du equals dx. So when you do that backwards power rule on that last term, let me rewrite out everything now. you do that backwards power rule, you get u to the minus 1 over minus 1, i.e. what that's going to leave you with is 5 times x plus 1 to the minus 1, or 5 over x plus 1. And that is the actual answer, the antiderivative.